Okay, let's, I think we are about to get started. Okay, so let's I guess get started. First of all, are there any, I don't think I have the daily problem up here, so I'm not going to talk about the daily problem just from here. Let's first start off, any questions about anything? Some people have asked, how do I turn in my homework late in a week? Well, in a week from now, right, this is my late homework. Okay, I'm using my extension, and you turn it in. Okay? Any other questions about this homework? Okay, that come to mind? Okay? Any other questions about graph algorithms? Shortest paths we talked about last class. Any questions about graph algorithms or anything like that? Okay, yes? The answer key should be posted. Has anybody seen evidence we have posted the second answer key? Then send me mail, because the answer is yes. I thought I had, and if I have failed, let me know. Okay? Any questions? Okay? Fair enough. Okay, so what I'd like to talk about is the daily problem for today, because today's daily problem is a particularly interesting and challenging one, which can actually, I think, be solved in a couple of different ways. But let's talk about it. The problem, if I understand it, is we are given a weighted graph, directed weighted graph, where all edges are positive. Okay, wait. We are given two vertices and an integer k. And we want to design an algorithm to find the shortest path from u to v that contains exactly k edges. Okay? So does everybody see what our situation is? We are given as input a weighted graph. Okay? Let's maybe construct a weighted graph here. Let's say this is vertex u, this is vertex v. This edge is of weight 1, 2, 3. Let's say, just to make it, let's say 2, 1. Okay? And we're going to ask ourselves, what is the shortest path from u to v using k equals, let's say, 3 edges? Okay? What is the shortest path from, first of all, what's the shortest path from u to w using one edge? What? Infinite. There is no such path. What is the shortest path of length of 2 edges? 3 is the length of that path. Does everybody agree with that? What's the shortest path of exactly 3 edges? Okay. In this case, I think ka-chunk, 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 5 looks like the right answer. Right? What's the shortest path of length 4 edges? Let's try this one. Does anybody have an idea of what the shortest path of 4 edges is here? Yes?
It's length 5.
You say 5, and what is it?
From u down the 2 edge, up the 1 edge, back up the 1 edge. And up.
Does everybody see 1, 2, 3, 4, 2, 3, 4, 5. There is a path using 4 edges of weight 5. Does everybody see that? So we are given a graph, we are given u, v, and w, and we want to find the shortest path with exactly that many edges. Okay? Any questions about the problem? Okay? Any question? It's a directed graph, so these edges have arrows. Now, it turns out if this, one way, I was thinking of it as an undirected graph. The problem is also defined on an undirected graph if we just replace each one of these by 2 directed edges, one going each way. Okay? So if I had every one of these as undirected edges, which was the same as having a directed edge going there and back, this is still a special case of what we were given. But we agree it's a directed graph. Okay? Any questions about that? Okay, maybe it'll make a difference, or at least, but that's an important observation. How can we find out if there is a path of length k in this graph? The shortest path of length k. Any ideas? This one actually is going to require several different ways of thinking about this. Yes?
Make a tree of depth.
So you're saying make a tree of length k, okay, showing every path of length k. Okay, let's think about this idea here. What he is sort of saying, I believe, is backtracking. Okay? So the tree, you're not talking about a tree as in a spanning tree. What you are considering is a tree of possibilities, right? That in one edge, you could go, again, if we give these things names, let's call these things A and B. Okay? You're saying you're going to start from U. Your next step you could go to is A or B. From A, you can go to U, or you can go to W, right? And from B, you could go to U, or from B you could go to W or U, right? Or A, right? Okay, very good. Okay, so and A can go to B. Where did I believe that? From A, I can also go to B. You're right. So you're making a tree of possibilities, okay? And what you're going to do is go down to a depth of k, okay, and then pick the shortest one. Is this algorithm correct? Yes. Okay. Is this algorithm efficient? Well, no, unless you find a better one. Once you find a better one, obviously no. Okay. What is the running time of this going to take? Okay, it should be clear it is going to be exponential in the principle in k. It is going to be something like the degree of the vertices raised to the k. Okay? And that is an exponential-like thing, and we'd like to avoid doing that. Sometimes we can't avoid doing that, which is why the next unit we will cover is on backtracking. Okay, where we will try to do this kind of thing as efficiently as possible. Okay? But for finding the shortest path of length exactly k, this seems like a hard thing, or a expensive thing. Any other ideas how we can find the shortest path of length exactly k? Okay. Any other kinds of ideas? Okay. Yes.
Can we have sort of keep track of stalling cycles? So like when we were making that path, we sort of stalled on that one edge. And so we can keep track of those, how we can stall.
So you're trying to say is if you want to kill time, find an efficient way to kill time. Yeah. Okay? And my reaction to that is maybe, but this sounds like a very specific thing to want to do. Okay? You're treating that as a special case of something. It'd be nice if we had a general case that found that, rather than saying that we're looking for stalling cycles and we have to think about stalling cycles as a concept. Okay? When I ultimately show you the solutions that I will come up with, I am not going to use stalling cycles as a concept. Okay? Any other ideas? Okay? Okay. Now, okay, any other ideas before I go into how I might think about this? Okay? Okay, so the way I would think about it is there are two ways to solve graph algorithm problems. One is by designing graphs. The other is by designing algorithms, right? I tell you it is hard to design algorithms, okay? So you have to worry about correctness issues. Is there a way I can design a graph such that I can use some garden variety algorithm that we already know to answer this question? Yeah? Okay, so you're wanting to make some connection to the squared problem, okay, and maybe, although that was an unweighted graph problem, right? So here we've got to worry about the weights on the graph. So there's a connection, maybe. That's finding, is there a path of length exactly k, okay? But it isn't helping me finding the smallest one, right? So can I design a graph that will solve this problem? And I want to propose the following graph. So I'm going to tell you two different ways. One is to design an algorithm. One is to design a graph. Okay? The first question is, what if I take my original graph, which was here, and I make k copies of it. Ka-chunk, 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 ka-chunk. These are my k copies of it, right? All the edges are going to look exactly the same, right? But what if I am going to encode, I want to take a total of k steps. What if I add edges so that at every step I take, I walk from this copy to that copy to that copy to that copy? Okay? Here is the end vertex in my kth copy. Does everybody see this? This is my start vertex in my first copy, right? What if I now, instead of reroute it, having edges, this edge go from here to here, okay? What if I instead add an edge, okay? Ka-chunk, 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 okay? From here to here of weight 1. Does everybody see kind of what I'm doing now? I'm going to say, here I have an edge of going from here to here of weight 2. Why don't I instead say ka-chunk, 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 ka-chunk here at weight 2? Okay? And now, what am I doing? Okay, every edge in this graph, I'm going to transform it. Instead of being a directed edge, you said directed, I like directed, going from one vertex here to one vertex here, it's going to go from this vertex to the vertex in the other copy. Okay? Thus, when I take this edge, I know that I have reached this vertex, and I have done it in one edge step. Does everybody see that? And now I'm going to do the same thing between this vertex and this vertex. This vertex here, I'm going to add an edge from this vertex that goes ka-chunk, ka-chunk, ka-chunk to there. Ka-chunk, ka-chunk, ka-chunk to there. 1, 2. Does everybody see what I'm doing now? Okay? I'm going to remove the edges within one stage of the graph and instead have it go to the second stage. And from the second stage, I'm going to do the same thing. I'm going to have a copy of all the original edges going to the third stage, going to the fourth stage. Okay? And I'm going to ask myself, what is the shortest path from this vertex to this vertex? Since all the edges are directed from this stage to that stage, they're all going forward. The shortest path from here to here is going to use exactly case edges. Okay? How many people understand this idea? Okay? Any questions? Like another question about, like, what is this idea? I don't get it yet. Explain it better. Yeah? Okay, let's try a good question. Okay, let's make a simpler graph just to make it clear what I'm doing. Let's say a 3-vertex graph. Okay? This is going to be, let's say the edges, this is A, B, C. This is of weight 1, 2, and 3. Right? Suppose we're going to say K equals 3. Let's say 2. Okay, I want to find the shortest path from A to C using exactly 2 edges. What is I going to do? I'm going to build a graph. I'm going to build a graph with 3 sets of 3 vertices. I think I'm going to need 3 because I want to go from time equals 0 to time equals 1 to time equals 2. So I'm using one more stage than the number of edges I'm going to use, because an edge has to go between 2 vertices, right? So now what is this going to be? This is going to be the vertex A1, B1, C1, A2, B2, C2, A3, B3, C3. There is an edge from A1 to B2 of weight 1. There is an edge from B1, B to C2 of weight 2. There is an edge from this to A3 of weight 3. Does everybody see that? See what my construction is? I'm now going to do the same thing from here to here. B goes to C. Okay. A goes to B. Okay. What is the other one? I guess C goes to A. The weight of this was 3. The weight of this was 2. The weight of this was 1. I want to know what is the shortest path from this vertex to that vertex. Okay? Any questions about that? How many people see the idea? Okay? So what's it? Okay, any questions about it? Yes? Well, what I'm guaranteeing you is, what do I know about the original graph? The original graph was a graph, okay? If I asked you to find the shortest path on that graph, I ran Dijkstra's algorithm on it, right? But how many edges did that shortest path use? However many edges it had to use, right? If here I want an absolute rock-ripped guarantee, the shortest path has to use exactly k edges. I want the shortest path that does use k edges.
So you're saying that every path is going to be k edges?
In this case, every path from here to here is going to be exactly k edges, right? Every edge goes from left to right, okay? It can't be any longer than k edges, okay? It can't be any shorter than k edges. Any path from here to here is exactly k edges, okay? And therefore, running Dijkstra's algorithm on this has to give you the shortest path with exactly k edges. Okay? How many people get that idea? Okay, any questions? Yes?
Why do you only connect A to B and not A to C?
Well, in this graph, okay, so because this was, she told me this was a directed graph. Okay? And on this graph, I am seeing it as a directed graph where it's just a directed cycle. If it was if there were other edges that went the other way, then I would have to do those connections, right? But the reason is because this is just a directed graph right now, for my simple example, right? Does everybody see that if I made this directed, if I added another undirected, if I added another arrow here, every arrow I add would add another edge in each stage. Okay? Any questions about that? Yes? So does it take more memory to do this, okay? The answer I'm going to say is, on one level, yes, okay? But right now, we're looking at it, right now, before this, you didn't have a way of, okay, let's think, how much memory does it take? How much memory is this going to take? The original graph had n vertices and m edges. How many vertices will this graph have? Yeah? K times n vertices. And how many edges? K times m. Okay, so is it going to take more memory? Yes. But do you have another algorithm for it? Your alternative was his backtracking thing, which was going to take exponential time, right? So when you tell me it's complaining about how much memory it's using, recognize that we now have a correct algorithm for solving the problem in polynomial time, assuming k is at all reasonable number. Okay? Any questions here? Okay? This is what I mean by design a graph instead of an algorithm. The correctness of this is obvious without using any proofs of Dijkstra and all this kind of stuff. Okay? Any questions about that? Okay? Now, what if you say, I don't want to design a graph, I want to design an algorithm? Okay? Let's look at another way of thinking about this thing, which is ultimately maybe going to be a similar kind of idea. First of all, any questions about this? Does everybody see how the data approach works? Okay, to give us the fast algorithm. Any questions? Okay? Now let's think about an algorithm for this. Okay? Now, what algorithm is there that we have seen for computing shortest paths that seems like it might encode something about the length of a path in terms of number of hops? Were any of the graph algorithms we talk about, was there something about that flavor to it? Yes? Floyd's algorithm had a k in it, but it was a different kind of a k. It turned out that was saying don't use this many use this subset of vertices as intermediaries. right? But there was an idea that maybe we could come up with a formula, a recurrence-like thing, that would govern this. So my question is going to be, can I come up with a recursive expression that would tell me what the length of the shortest path is of length k? Let's say that I want to figure out what is the cost of the shortest path from vertex u to vertex v of length k. Okay? Is there any, remember, think of it like Floyd's algorithm. I'm storing these things up to be used. Is there any way I could compute what the shortest path from u is to k is, to v is, of length k, based on things maybe that are of length less than k? Okay, yeah?
Well, we can start with the base case. The cost of going from u to v using exactly one edge is the cheapest edge from u.
Okay, so the cost of going from u to v of u to v in using one edge. So what you want to say, you've got a basis case. You want to say that the cost of going from u to v, okay, u to v, I'm probably going to regret this, uv of length 1 is going to be exactly the weight of the edge from u to v. Is that correct?
Yeah.
Okay, fine. Okay? Now, in general, is there something I can use for smaller k that will help me tell it for actual k? Can anybody see this kind of thing? Okay? My claim is that the cheapest way to get from u to v using k steps is going to be the cheapest way to get from, okay, u to somebody named x in k minus 1 steps plus the weight of the edge from x to v. Okay? If I say what is the shortest, if I knew what the shortest path was using k edges to get from u to v, that had to have used the shortest path to get from u to some vertex x using k minus 1 edges, and then use the direct edge as the last thing. Right? Does everybody kind of get that idea? If so, which vertex x should I use? Which is the right previous vertex to u, v? The one that minimizes the cost of everything. So I'm going to claim that if I take the min over all x from 1 to the number of vertices n, I pick which vertex is it that minimizes this. Okay? Then I claim I have it. Okay? Look at this for a second. Actually, when we get to dynamic programming, we're going to be doing this kind of thing all the time. Okay? And this is actually not a complicated one. So maybe this is worth looking at. If you don't get it, you'll get a chance to see it later. But understand the idea here. The cheapest path from u to v using k edges is going to have to use end on an edge going from some vertex to v, and it's going to use the cheapest path from the start vertex to that vertex that uses k minus 1 edges. Okay? So if we had this sitting in a table, like Floyd did, right? And we have this sitting in the adjacency matrix, which we can have, this gives us a way to do it. Yes?
But wouldn't we have to find x along the way anyway? So finding x would also take a large number of steps, wouldn't it?
Well, how many steps is this going to take? So first, do you see that this is a true statement? And that this is a true statement for any pair of vertices u and v, and for any distance k. Does everybody agree with that? So how much time does it take to find this thing? Let's think about it. How many choices are there for the first vertex? N in general, right? How many choices are there for the second vertex? In general, there are n of them, right? K is going to be a number that's going to go from 1 to the actual number we're searching for, right? So there are something like n squared times k of these cells. Okay? How much time does it take to fill one of these in from these values? To fill this in, we're going to have to try every one of these n intermediate values, right? Look this up in it. Once we fix what x is, we look this up in a table, and add it, right? So how much time is it going to take to compute the sum of this plus this? Is it 1? Is it n? Is it what? The sum is constant, and how many of these sums are we going to want to compute to figure this out? N of them. So in n time, we can fill in one of these cells. And in general, there are n of these n squared times k of these cells. This would be the running time of the entire algorithm. Would be something like n cubed times k. Okay? Any questions? Okay? How many people think a question? Yes. Well, because there are this many cells to fill. Do you agree? And how much time does it take to compute the answer from this? You're going the min of n things, right? Okay, we will do more of this. So if you don't see this, don't be frightened. Okay? But how many of you do think you see it? Okay? Hold that thought for about a week and a half. Okay? Because this is the kind of thing that we will be doing, and it's a wonderful technique to know about. Okay? Because you can do, in some sense, if you look at it, this whole algorithm, I'm telling you, is this one line of formula. Okay? So once you understand it, this is not that hard a thing to do. Okay? But basically, we came up with a recursive formula for the answer. And a way that, just like Floyd's recursive formula, we could compute it quickly if we had the smaller values. Okay? Any questions about this? You can build the graph and use the famous algorithm you know about. Or you can use this particular dynamic programming technique, which we haven't taught yet, okay, to design an algorithm for it. Which is better? Well, that's up to you. I personally find it better to design data graphs rather than to design algorithms. This required some smarts. The other one didn't really require smarts. Okay? Once you saw it. Any questions? Any questions about this problem? This is a good problem of the day, so I do want us to, I'm happy to answer some questions about it. Any questions? Okay? Yes? Could you do it recursively and just make this a recursive program and not worry about storing it? The answer is yes, but at that point you're no better than he is. Okay? It turns out what you're doing is a recursive search that's basically going to be exponential. Okay? So there is a difference here. Okay? So you're right, this is a recursive thing. He was doing a recursive thing. Okay? If we did his in an unbridled way, certainly it was exponential. But I am actually doing it in a way that actually turns out to be bridled, okay? That kind of, I can bound how long it's going to take. Because I'm storing things rather than recomputing them. He is going to blindly recompute certain things. Okay? Any questions? Okay, any questions about any of this? Okay, good. So that said, it is occasionally quite important to be able to do what I will call exhaustive search. I was complaining about him using exhaustive search. The only reason I was complaining about him using exhaustive search for this problem was that, in fact, there is a better algorithm. I showed you a better algorithm, right? Now, for a lot of problems that we have talked about, the world is NP-complete, the problem is NP-complete, and there is no better algorithm in the worst case than searching for things. And so being able to search as efficiently as you can is an important thing to be able to do. And so for that reason, I'm going to want to talk here about backtracking for the next couple of classes, okay? Because that's the technique for efficiently searching if you want to get the exact solution to a problem. Where no clever, fast algorithm exists, backtracking is basically what you have to do. And it can be amazingly effective if you are clever about how you do your search, okay? Backtracking and exhaustive search is one of the oldest things in computer science. And it's kind of, historically kind of old-fashioned algorithms. I can tell you that in recent years in the algorithm world, they call it now exact algorithms. Algorithms that basically efficiently search through all possibilities are performing very, very well. People have figured out ways of doing this kind of search so you can do surprisingly big problems exactly. And so this is an interesting thing. Okay? Any questions about it? Okay, fair enough. Ka-chunk, ka-chunk, ka-chunk. So I would like to motivate my talk about backtracking by talking about Sudoku. How many people here are familiar with Sudoku? Almost everybody, okay? It used to be that when I would teach in class, everyone in the back of the room would be doing Sudoku while I was teaching. Now I gather they've switched to Facebook or something like that. Okay, so it may have changed a little bit. But what is Sudoku, okay? Sudoku was, you were given this partially filled in grid of numbers, and there were constraints about what numbers could be, how the numbers could be arranged. You wanted to insist that every row had to have the numbers 1 through 9 appearing once. Every column had to have the numbers 1 through 9 appearing once. Every one of these boxes had to have the numbers 1 through 9 appearing once. Okay? And the goal was to take a partially written board to a filled out complete Sudoku board. Okay? Anybody, how do you do Sudoku? Okay? Yes?
Well, there are certain heuristics you can use that will help improve the state of the board somewhat.
Okay?
Like, for instance, you'll start by looking for cells that can only contain one number.
So in a dream, what you would like to have is that there might be a position on the board where the other numbers constrain you, so you can only put down one of them. What are the possibilities for this square? It can't be 1. It can't be 2. It can't be 4. It can't be 6. It can't be 8. Okay? Does everybody see that? If it was only one possibility, you could put it down. If it were two possibilities, though, what did you have to do if there were two possibilities? Okay? Somebody, okay? What would you do if there were two possibilities? Yeah?
If there were two possibilities, but you didn't know anything else, like there weren't any clues to which one it was, then
Yeah.
you have to fill in other squares before filling in the next one.
So you're saying you fill in other squares before that one, or, yeah, or you write it in pencil, right? There was only one possibility, you could write the answer in pen. If not, you wrote the answer in pencil and then kept going. And if you found that there was some contradiction later on, you said, no, I made a mistake, right? And then you backtracked by erasing all the pencil. Is that right? And you put in the other possibility there. And then you could put it in pen, maybe. Okay? Any questions about it? So that is what you were doing with Sudoku, is the basic thing that you are going to want to be doing with backtracking. Okay? Any questions about that? Okay? So again, what have we been saying? Sudoku is exhaustive search of all possibilities. Using constraints by eliminating possibilities enables us to prune the search so we don't have to search all possible numbers at all possible places. And in fact, the wonderful thing about Sudoku is the search can be pruned enough that you can do it in the back of my class during a lecture, okay, by hand, instead of needing a powerful computer for it, okay? Does everybody see that? Okay? And the key to doing it, so that you correctly do all possibilities efficiently, that is the idea of the backtracking algorithm. Any questions about that? Okay, so let's talk about what is backtracking. And there are different ways, perhaps to implement it or to think about it. I'm going to show you my particular implementation and how I think about backtracking in general. I am going to say that backtracking is we're going to systematically search through a space, okay, where we are looking for a solution. And what's going to be the case here is backtracking is going to be a specific algorithm which you are going to instantiate, customize to your problem by basically implementing 3 subroutines, okay? And, you know, what we're going to do is we need to have a representation of our solution. I am going to view the representation as being what I call a vector. An array is the right word here. You like the word array better than vector? It's the same thing, okay? We're going to say that the solution is going to be an array of things, okay, where each element is going to come from a finite set of possibilities, okay? And what we are going to do is to build the solution left to right by adding another element to the end of the solution. Let's think about the traveling salesman problem. What is a solution to the traveling salesman problem? Remember that you have a graph, you want to find the shortest path. What is a solution to the traveling salesman problem look like? Okay, anybody? Yeah? It's like a what? Okay, you're saying try every possibility. You're giving me an algorithm. What does the actual answer look like? Yeah?
It looks like a path from vertex to vertex.
It is a sequencing of the vertices, where ultimately you have n vertices, and each vertex appears once, right?
Right, and the last vertex is kind of implicit.
So what my solution is going to be is my first choice is going to be a vertex. My second choice is going to be another vertex that you can reach by one edge from this and isn't the same vertex as before. Does everybody, because then I would have a repetition, right? So my claim is that I can build up a traveling salesman solution by basically an array of vertices, okay? Any questions? And I'm going to build it up as a partial solution, trying to grow it and make my tour longer and longer if I can. If I find there is no way I can extend my tour so far, I'm going to say, whoa, I made a mistake. I'm going to knock the last thing off my tour, take a backward step, and see if I had any other choices for that slot. And if so, move into another direction. Okay, that's the basic idea here. Okay, I'm going to represent my solution by an array. Okay, any questions? Again, the idea of backtracking. Okay, again, I'll show you the implementation in a minute, and you'll see, that'll make it more clear. But the idea here is that at every step, I'm going to be given a partial solution, meaning I have filled in some things from my solution, the first 5 vertices of my tour. I am now going to look for what is the 6th vertex of my tour. Okay? There are going to be a set of possible 6 vertices for the 6th spot. They can't be, in the case of traveling salesman, anything I have already visited. They can't be a vertex that isn't adjacent to my last vertex. Okay? That will leave a set of possibilities. I will construct a set of possibilities and one by one insert it at the end of my path, tour. That will make a bigger partial solution. And I'm going to see whether this can lead to something. If it can't, eventually I will backtrack to this place and try my next possibility in the 6th position. Okay? So the basic things I need to do, I need to be able to figure out what the possible solutions are for the kth position, what the possible elements for the kth position are. I need to be able to check whether when I extend it, what I have is still possibly going to lead me to a solution. Okay? And I have to check at the end whether or not I am done. Okay? And then if I'm done, I've got to go do something. Any questions? Still maybe a little too abstract. Okay? But this is the idea here. Here is pseudocode for what backtracking is. Okay? I'm going to show you real code in a minute. It's not going to look that much worse. Okay? But this is the basic algorithm. My arguments to backtracking are that I am given A is my vector of a solution. K is how many spots in this vector have I already filled in. Okay? My first thing is to say is my vector right now the solution that you're looking for? If so, I should do something with it. Print it, ring a bell, whatever you want to do when you find the solution. Okay? If not, I want to know, is it possible to extend my partial solution so far into a full solution? I'm going to now say, okay, my next position I'm going to fill is the k plus first position, so I bop k up by 1. I am going to consider what are the possible elements that can go into the k plus first slot of my array. What are the possible next vertices I can go? What are the possible next things I can add to lengthen my solution? So long as that set is not empty, I am one by one going to take that element, take that set, pull out one element of my possibilities, put it in the kth position of my solution, delete it from the set of possibilities because I've just tried it, and now resume my search on the larger partial solution, which means that because k is now larger than it was when I called, and A now has an extra element in it. And I'm going to recursively call backtrack on this thing. One of two things is going to happen. Either in the course of this recursive call, it finds a solution based on what I've done. Or if not, eventually it'll bomb out and come out of this. At which point I go back into my loop, and I now see, is there another candidate for the kth possibility, which I had? If so, try that in the kth slot, and try searching from then on. Okay? Any questions about that? How many people sort of see it? Sort of. Okay? Any questions? Here, okay, so what is the idea? I'm going to show you the real code in a second. But there is one big idea here. This is the exact same algorithm as depth-first search in a graph. Remember we did depth-first search in a graph? What was depth-first search in a graph? You started in a vertex, right? You said, let me go through any vertex that what are the possible next things I can go to? It's any edge that goes to a vertex that has not yet been discovered, right? I go through this edge. Have you been discovered? I've been discovered. Have you been discovered? Not been discovered. That's my next thing. I'm going to go step forward, having made my tree bigger, and start exploring and wander around there. And eventually, in the recursion, I'm going to bomb back to the loop here and look for other outgoing edges from this vertex. Okay? The same idea here as depth-first search. Okay? The only difference is backtracking is depth-first search on the set of configurations, the set of partial solutions. That's really what it is. If you built a graph where the vertices were partial solutions, partial prefixes of the vector, then basically depth-first search on that graph is going to be backtracking. Any questions about that? Okay. And depth-first search was interesting because it guaranteed we visited every vertex. That was one of the things that was interesting about it. So we knew that if there was a solution, we were going to find it. And it was also efficient because it didn't visit anything more than it had to. Okay? Any questions about it? Do people sort of see the connection to depth-first search? Any questions? So what is the subroutine when you really implement it? This is my C language generic used for everything backtrack implementation. It is one crummy screenful. Okay? What is it doing? It will solve any backtracking thing, including your homework problem, which we will get to by the end of the day. Okay? If you instantiate it with the right 3 subroutines. What are those subroutines? There is a subroutine here called is a solution, which basically is going to test whether or not your current vector is a solution to the desired problem. Okay? There is a subroutine called process solution. Once you know that you have a solution, what do you want to do with it? Do you want to print it out? Do you want to ring a bell? Do you want to count how many solutions there were? If so, in process solution, simply add 1 to that counter. Okay? And there is a third thing, construct candidates, whose job it is to take the current array contents, the A content, and figure out what possible positions are there, okay, for the kth spot, okay, for the next spot in the array. And then what is Backtrack going to do? For each one, it's going to fill out an array of candidates C, of which there are a total n candidates of that array are useful. What is it going to do? For each candidate, it's going to copy the ith candidate into the kth slot, do a backtrack search from here, and I have actually, in this case, I have a Boolean variable finished. If I want it to die, okay, once it's find its first solution, maybe I'll set a Boolean thing that said that if you want me to stop searching now, I'm going to bomb out of it. Okay, there's a global variable. But basically, what is the idea? One by one, I'm going to try a new element, and I'm going to do a backtrack search from here. This is the recursion. Backtrack AK input, calling from AK input. Okay? Any questions about that? A is the solution vector. K is how many slots in that vector are filled already. Input is any auxiliary information that you want to carry around to these is a solution, process solution, or construct candidates functions. Okay? Any questions about that? Okay, any questions? So when I think about backtracking, I don't really think about this algorithm. I think about what are, when I want to apply backtracking to something, what are my implementations of these functions going to be? Okay? Is a solution. It took my array, my solution, partial solution, the k, tell me how many the first k elements are. How would I tell? What would is a solution be for traveling salesman? Let's think about it. Okay? If I'm looking for a tour, when is a tour going to be interesting? Okay? It is going to be a tour when it visits every vertex, right? Exactly once. So what is a solution going to be? Something like, okay, is k equal to n? And has every vertex been visited exactly once? There's no repetition. That might be what is a solution is. Okay? Any questions? We'll see more examples, but let's make sure we understand it. Construct candidates. What are the possible candidates for the kth slot? Okay? Given that my array has filled up the first k minus 1 things. So give my problem. I've got a partial solution. What are the possible candidates for the next slot? Give me a complete list of these things. Okay? And the third one, which is process solution, means now that I have the complete solution, something that you called a solution, what do you want to do with it? Okay? Any questions about that? So when you're using backtracking, you can use my subroutine, and all you need to do for any problem in the universe is specify these 3 subroutines. Any questions? Okay, good. Kabunk. So let's look at the first canonical application of this, okay, which is constructing subsets of things. Okay? Suppose I'm given n elements. How many subsets of n elements are there? Okay, how many distinct, let's say you want to construct all possible subsets of an element. Let's take, maybe we'll go to the screen now. What? Does order matter? That's a good question. Yes. In a subset, I guess no. Order does not matter. So, which to me means that we want to know the distinct groups of elements. The order of them doesn't matter. So 1, 2 is the same as 2, 1. Okay? So I want to know, if I give you 3 items here, 1, 2, and 3, how many different subsets of those items are there? Yeah, somebody with a hand? 2 to the n is what I'm hearing. Okay? So you're saying that would be 3, it would be 2 to the 3 or 8 subsets, right? What are the 8 subsets of this? Okay? You want to say the empty subset? 1, 2, 3. 1, 2. 2, 3. 3, 1. Well, what do you mean 1, 3, I guess? To be okay. 1, 3, yeah. 1, 2, 3. And which did you forget? None of them, because hopefully it's straight out to 8, right? 1, 2, 3, 4. But recognize that when you list any of these things, that's a dangerous question, right? Because you're listing them and you think, oh, gee, I got them. You're not necessarily listing them in a systematic order, right? In order to make sure you didn't miss anything, you'd better list it in a systematic order, right? Does everybody see that these are the 8 possible subsets of 1, 2, and 3? Okay? And when I say constructing all subsets, I want to make sure that I can construct them, okay, so that I see each subset once, okay, exactly once, okay? Any questions here? That's what my problem is, okay? How can I represent, let's now think about my problem of constructing subsets. I am going to use an array A, we said. Here's my array A. How long should my array be, and what should the elements of my array be to represent a solution? Okay, there are different answers to this question. Okay? Now, let's say I want to generate all subsets. How are you going to represent a subset in an array? Okay? Let's try it. Does anybody have any ideas? Yeah? Well, a list. Okay, I'm representing it in an array. But how am I going to encode a subset within an array? How am I going to describe it? What are the elements going to be? Okay? Sounds like maybe it's too basic a sounding a question. Yeah? So there are ways, there's 2 different ways that we could do it. The way I kind of like doing it is that I'm going to have an array of length n, and I'm going to have a bit, every element is going to be true or false. And that if I have, in the case of a 3-element array, if I had the elements true, false, true, what subset did this correspond to? 1 and 3. Does everybody see it? He's saying that true in the ith position means that element I is in the subset. Okay? That is the way that he wants to represent it. And see that that's a perfectly fine way to represent this, right? Because I have got an array A, an array of positions, where each position is a finite possibility. Okay? So this is one way I could do it. Okay? In fact, the way I kind of like to do it. Could anybody come up with an alternate representation of a subset? Yeah. Oh, okay. So wait. So first of all, linked list is the wrong idea here. Recognize though what I'm trying to think about. There are candidates for each spot. The actual solution is going to be the first k elements of some array. That is what we are restricting ourselves to doing. Okay? But there are different ways we could represent this thing. Can someone come up with an alternate way to represent the array subset 1, 3 in an array? Yeah?
Could you use a tree or a graph? And what you can do is you can limit yourselves on how many different edges you can use to get from point 1 to point 2.
Okay, I want this representation to be an array. We're not dealing with graphs. We're not dealing with this. What I'm thinking about is how, I'm looking, maybe it's not a representation. Suppose I told you the word was encoding. I'm looking a way for you to describe to me a subset. You could describe the subset 1, 3 by true, false, true. Is there any other way you might think of describing it? Okay? Yeah? So you tell me 1, 3. Okay? I could alternately perhaps represent the subset by the element 1 followed by the element 3. Does everybody see what that possibly could be? What? No. Okay, what I'm going to do, okay, let's think about this. What I'm going to be doing is, A is going to be where I am storing my solution. I am always going to be overwriting my solution. Okay? So I'm looking for here an encoding. When I talk about my problem representation, I mean what is the encoding of the solution that I'm looking for? Okay? I want to claim I could represent the subset just by listing the elements of the subset. That's all that I'm trying to say. Alternately, I can represent it by trues and falses. Okay? It turns out that trues and falses are easier, and so that's what I'll talk about. Okay? Any questions about that? That didn't quite go the way I wanted it to go, but that's what happens on live television. Any questions here? Okay, yes?
So, isn't the solution supposed to be a set of subsets?
Okay. So what you're, okay, so now I think I understand what you're saying. You are telling me that, I'm saying that I want to construct all subsets. Isn't the solution the set of subsets? And I'm going to say the answer is no, okay? What I'm going to do is one by one construct subsets. When process solution says that, when it says is a solution is true, now you have the next, let's say, subset of your choice. If you want a list of subsets, now you copy this thing out. Okay? So my vector is going to represent one element of the solution space. Okay? And if you want to enumerate, print out all subsets. Whenever I have filled an array with something, and is a solution tells me this is a solution, then you add this to, if you want all subsets, add that to your separate data structure of subsets. We're building up one thing at a time, and we're going to be overwriting it over and over. Okay? Any questions about this? Does that clarify your, okay, any questions here? Okay? Good. Okay? So let's think about this for a second. What is, suppose we're going to represent, okay, as I said here, we're going to represent, I'm going to take a, let me take a chance with this thing. Suppose we're going to have some vector here. Here's our solution A. Okay? We are going to build up our string of trues and falses for each subset. Okay? Does everybody see we've got an array of up to n elements here? Okay? Under what condition is a partially filled vector of trues and falses? When does it represent a real subset of n elements? Okay? The answer is going to be when it has n true and falses in it. Okay? What are the choices in general for the ith spot in the array? Okay? What are the possibilities I can have there, my candidates? If I am using this binary representation, what are the possibilities for that spot? Yeah? True or false, right? And what do I do when I have a subset? You wanted to add it to some data structure. I, let's say, just want to print it out. Okay? So let's look at this thing. Let me show you how I'm going to instantiate this. Kabunk, 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 kabunk. My question of is something a solution is simply going to be, is K, okay, the slot that I'm filling, the same as the number of elements that I am trying to, of the size of my universal set? Okay? If so, I've set every element in my solution to be either true or false. It's going to describe a particular subset. Construct candidates. The candidates for the kth position, in this case, are independent of all the candidates before them. For the kth position, it can always either be a true or a false. Okay? Any questions about that? So this is simply what my construct candidate solution is. Okay? And my process solution. Here what I'm doing is simply printing out the numbers that are in my set. If A sub I is a vector of n elements, and the ith value being true means element I is in the subset. What is my solution? Basically, for I goes from 1 to k. If A sub I is true, print out I. Okay, that wasn't here, right? Print out I. Okay? And then it's going to print out the numbers one after another that are in the subset. Any questions about that? Let's think about this. What is going to happen when I try to compute all subsets of size 3? Let's stop and think about this. Maybe we'll do this on the board. Okay? Suppose I want to compute all subsets of size 3. Okay? I am going to have a vector of size 3. This is what my thing is. What are my candidates for the first spot? What are they? True or false? Okay, and which did I put first, true or false? Does anyone remember in my code which I did? Let's say I put true first. Let's start with true, right? What am I going to do? For each of my candidates, I'm going to pull one out and put it here. And now ask myself, is this a complete subset solution? No. So what am I going to do? I'm going to call backtrack and say, now, given that there's a t here, what are the choices for this spot? What are the choices? True or false. And what am I going to put in there as my first choice? True, right? And now I'm going to go call backtrack and say, what are my choices for this spot? And what are my choices? True or false. And I'm going to put a true here. And I'm going to ask myself, is this a solution? Yes, it's filled up the array, so it is a solution. What solution is it? I now will call process solution if I want to print out the subset. What subset is this? This is 1, 2, 3. Does everybody agree with that? What is my next thing that I'm going to do? I am going to replace this thing. I try to extend it. I can't extend it. I now am back in my loop. I'm now going to try my next choice here. Okay? Is this now a solution? Yes, okay, we're going to do this interactively. Yes. What solution is this one? It is a 1, 2 solution. And now I'm going to pull that out and ask myself, well, what's the next solution element for this spot? There is no next element, right? It is now empty, so my backtrack is going to bomb back to here, right? And now what's my choice going to be for this one? Is this now a solution? No. But I now call backtrack and find out what are the candidates for this spot? True and false. Does everybody see that? And I pull the first one off, and I put in a true, and I ask myself, is that a solution? Yes. What solution is that? Which solution is that? 1, 3. And I now see, can I extend it? No. Okay. What is my next choice for this one? Well, I can make this a false, right? Does everybody see that? Is this now a solution? Yes. Okay. And what solution is this? 1. Okay. Is there any other possibility for this choice? No. Backtrack. Is there any possibility for this choice? No. Backtrack. Is there any other possibility for this choice? Yes, there is. Is this a solution? No. What possibilities are there here? True and false. What's the first one I try? I put in a true. Is this a solution? No. What are my possibilities for the next spot? True or false? I go through my first candidate, true. Is this a solution? Yes. What solution is it? Okay. What solution is this one? 2, 3. I now replace it. Okay. What is my next choice? This is a false. Is this a solution? Yes. What solution is it? What solution is it? 2. Okay. Is there any possibility left here? No. Is there any possibility left here? Yes. False, right? What are my possibilities here? True or false? Okay. If I put in a true, is that a solution? And what is that solution? 3. And then I try the other possibility. Is there a put in a false? Is that a solution? What is that going to be? Empty set. Is there any possibility left here? No. Is there any possibility left here? No. Is there any possibility left here? No. I am done. And these are the 8 subsets listed in that order. Any questions about that? How many people see the flow of execution here? Any questions about it? Okay. It is important that you be able to go through the examples that we're doing here so that you can see what the flow of this execution is. Okay, because if not, you're going to be hopelessly lost. Okay, when you do it. Okay, and again, how did we call this thing? We called it by backtracking. On A, we want to fill up n slots starting in the 0th position. Any questions? Now, let's look at another application of backtracking. One that I can tell you is going to be critical to your next assignment. Okay? Is something called permutations. How many permutations of n things are there? Okay? N factorial. How many things for n equals 3? How many permutations are there for n equals 3? 6. What are they? 1, 2, 3. 1, 3, 2. 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1. Okay? I can do that because I'm doing it systematically. Now, if I want to represent a permutation in an array A, what is a logical representation for me to represent an n-element permutation? How many slots should my array have? N. And what are my choices for the slots?
Any of the n elements.
Does everybody agree my candidates are presumably going to be the numbers 1 through n? Right? Is it going to be 1 through n for every position? No. No, why not? What is going to be the choices for my 3rd position here? It will be the numbers 1 through n, less what number is in the 1st position, less what number is in the 2nd position. Does everybody see that? So if we're looking to fill up an array, okay, fill up a solution, we're building up our permutation one step at a time. The choices for the kth spot are going to be the numbers 1 through n, less the elements that appear in the partial solution so far. Okay? Because suppose I had already put 3 and 1 in the partial solution. If I put a 3 in the third spot, am I possibly going to end up with a permutation as a result of that? No. Okay? So my choices here are the numbers 1 through n, less the ones I have used so far. Okay? Any questions? This is the sophistication difference from the previous problem. Any questions? So what is my solution going to be? Okay? I claim that my candidates for the kth spot are simply going to be the numbers 1 through n, less any value I have currently used so far in A. How did I do this? I mean, that's easy to say. How did I do it? Well, the way I did it was I set up a Boolean array with n elements, and I said the ith value was definitely not in the permutation. I went through the first k elements of my permutation and said if a sub I is, whatever a sub I is, okay, that element I can't have in my permutation. So I say in perm sub a sub I is true now. My candidates for the next spot is every element from 1 to n that hasn't appeared in the permutation. If in perm is false, then the ith element is one of my candidates, and I'm going to add it to my set of candidates and bop that up. Any questions about that? Do people see that this is constructing all numbers from 1 to n except the ones that appeared in A so far? Any questions about that? Okay. What other things did I need? Okay. The other things that I need are, I need to be able to stop when I have filled up, again, all n elements of my array have been filled up. That's when I have a full permutation. And then what do I want to do with the permutation? In this case, I just want to print that out. So I'll say 4i goes from 1 to k, print out a sub I. Any questions about that? Does everybody see how I have used these three functions to instantiate it so that I put out permutations? Any questions? Let's look at the example now. Let's go through the execution very, very quickly. Okay? What is going to happen? Suppose I want to construct all permutations on three things. What are my candidates for the first one? Spot. What are my candidates? What are they? 1, 2, 3. I put in a 1. What are my candidates for the second spot? 2, 3. I put in a 2. What are my candidates for the third spot? 3. I fill that in. That's my first solution, right? I backtrack. What's my next candidate for the second spot? 3. What are the possibilities for my third spot? 1, 2, and it's got to be 2. I put in a 2 and I am done, right? I have no more possibilities for the second spot. No more possibilities for this spot. What's my next possibility for the first spot? 2. Now what are my possibilities for the second spot? 1, 3. I put in a 1. What's my next possibility? 2, 1, 3. Nothing else to do here. Put in the next one. 2, 3. What's my other possibility for this spot? 2, 3, 1. Nothing else here. Nothing else here. This becomes a 3. What are my possibilities for the next spot? 1, 2. Put in a 1. What's my possibility for the next spot? 2, 3, 1, 2. Now I replace that. Nothing else here. 2 is still here. What's my possibility for the last spot? 3, 2, 1. Nothing else here. Nothing else here. Nothing else here. I am done. Those are all permutations. Any questions? Any questions about how you construct all permutations? It is good because that is what you are going to be doing for your next homework, okay, in a little bit more sophisticated guise. Okay, I'm going to pass this out now. I'm going to talk about this very, very briefly, and we will resume next class, okay? But what is this problem going to be? This is the homework 4 problem, where everybody has to work individually. The goal is I am giving you an NP-complete problem, which turns out to be involved with permutations, okay? That your job is to write the fastest program to find the correct solution to this problem. I'm not going to even tell you what the problem is because we don't have enough time. But I want to just put your head into the matter. Next class I will tell you these things. But let's just think what the goal here is. There is a problem which turns out that the problem is called bandwidth. It involves graphs. It involves permutations. And what you're going to have to do is one permutation of the vertices is the best, okay, solution to this problem. Your job is going to be to search through all permutations and find which one gives you the best solution. That's the basic thing. Now, I am going to be giving you a bunch of examples here. All of you are going to have to try the examples, and your program is going to be graded by how big an example you can solve in 1 minute of running time on your computer. Okay? And the winning programs, we will have a trial, a contest, and the winning programs will win a prize. For the fastest ones, the slowest programs will also win a prize, but you don't want that one. Okay? Any questions here? Okay? So the goal here is I want you, what can we do? I know we've only got 3 minutes. I don't want to overwhelm you by talking about the problem. But I want to tell you how to think about it now. Okay? This is going to be one where you're going to have to search through all permutations and pick the one that is somehow best. It is going to be backtracking. If you did the backtracking just like I described here about permutations, you will come up with a correct program. In this assignment, you need to come up with a correct program. To get full credit, it's got to be fast. Some of you may say, oh, I can come up with something that's going to find close to the right solution, but won't always find the best solution. That program is called wrong, and no credit will be given for wrong solutions. Okay? In fact, I can tell you if anybody's program runs too fast, I will know your program is wrong. Okay? But we'll talk more about that now. For next time, what do I want you to do? I want you to read through the assignment. I want you to try to understand what a bandwidth problem is. And I will explain that to you next time. Okay, thanks for your attention. See you guys then.